This tutorial will be discussing chemical properties of trialcylglycerols. In hydrogenation reactions, double bonds of unsaturated fatty acids, remember those are the ones with the double bonds, react with hydrogen gas. We've done these reactions before. Notice that hydrogen is actually in the word hydrogenation, so that's a good visual image of what's going on here. To produce carbon-carbon single bonds. So you're breaking the double bonds and you're adding hydrogen to make the single bonds. Hydrogen gas is bubbled through heated oil, typically in the presence of a nickel catalyst. So here is a unsaturated bond. We have the double bond right here, and we're reacting it with H2. So H-H. What's happening is those hydrogens are then being bonded to those carbons, and that double bond is breaking in the process. So notice we have 7, 14, 15, 16, 17, while here's 1 and 16. So they've actually combined the number of carbons here when they rewrote it with that single bond. In commercial hydrogenation, the addition of hydrogen is stopped before all the double bonds of the liquid vegetable oil is completely saturated. The partial hydrogenation of liquid vegetable oil changes it to a soft, semi-solid fat. That's why margarine is more spreadable than butter. The more saturated the product, the higher the melting point, which means the harder it is, the more solid. So the more double bonds you have, the softer it's going to be. Unsaturated fatty acids can be cis, which gives us that kink, which interrupts the interactions between the bonds, between the two compounds. Or it could also be trans. This is on opposite sides. Now notice the way that this looks in comparison to this. These are all single bonds. Now let's go back to that original picture. Notice that they both have that zigzag formation. This means that when it's trans, it can interact more with the saturated compounds, and more so than the cis. During hydrogenation, double bonds are converted to single bonds. A small number of cis double bonds are converted to more stable trans double bonds, causing a change in the overall structure of the fatty acids. In the body, trans fatty acids behave like saturated fatty acids and are estimated to be 2 to 4% of our total calories. They raise the low density level cholesterol and lower the high density. The LDL is considered the bad cholesterol. The HDL is considered to be the good. So the trans fatty acids. So here is the initial double bond, and it's going through hydrogenation by adding that H2. So those hydrogens are being bonded to it. Now a couple of things could happen. Either this H2 gets popped back off and it forms the trans, or it stays put and it forms a saturated. Foods containing naturally occurring trans fatty acids include milk, eggs, and beef. Foods that contain trans fatty acids from hydrogenation include deep-fried foods, bread, baked goods and cookies, crackers and chips, stick and soft margarines, and vegetable shortening. Let's move over to hydrolysis. In hydrolysis, trialcylglycerol is split into glycerol and the fatty acids. You may remember this from reactions of esters, where we recreate the alcohol, and that carboxylic acid. So basically you're taking water here in the HOH format, and you're breaking these bonds to form the original pieces. In saponification, this is the reaction of a fat with a strong base, such as sodium hydroxide, in the presence of heat. It splits trialcylglycerols into glycerol and the sodium salts of the fatty acids. Remember, the word salt means ionic compound. So you may remember from saponification before that would have an O minus and A plus. That happens again here, but now we're just doing it with fatty acids instead. So you're going to have a really long carbon chain coming off of it. Saponification is the process of forming soaps. This is how we form soap. With NaOH gives solid soaps that can be molded into different shapes. With KOH gives softer liquid soaps. So if we look here, this is saponification and soap. So once again, we're going to break it between the oxygens. So this bond here breaks at the ester. On one side, you're getting that alcohol back. On the other side, you have that O and A, which was the salt of the carboxylic acid. What's going on when you wash is that this here is nonpolar. It mixes with the oils on your skin and the dirt on your skin to interact with it, because remember, it's nonpolar. It's not going to react with water. It's going to react with oil. So this part of the chain reacts with the oil. Then this here actually reacts with the water, and as you rinse off your face, this goes down the drain as it reacts with the water, and it takes the dirt and oils that were on your skin with it. So here's a summary of all the reactions. Esterification was when we made the ester in water. So this is where we're making the trialcylglycerols. We had 3 fatty acids, 3 carboxylic acids, glycerol as your alcohol, and that's going to make your trialcylglycerol. For hydrogenation, we have the unsaturated fats, the double bonds, as your alkene, reacting it with hydrogen. This time we're doing a nickel catalyst, making a saturated fat, an alkane. For hydrolysis, we have the trialcylglycerol. This is reversing the esterification, and we're reacting it with water. The trialcylglycerol is your ester, and you're reacting it with water, and it's creating 3 fatty acids, which are carboxylic acids, and alcohol, which is actually the glycerol. Then finally, we have saponification. Once again, we have an ester. This time our ester is going to be trialcylglycerol. We're reacting it with sodium hydroxide. We have 3 of them because the trialcylglycerol, we have 3 carboxylic acids that have reacted there, 3 fatty acid groups. The sodium salt of carboxylic acid, the sodium salt of fatty acid, because remember, the fatty acid is a carboxylic acid. You're left over with alcohol, and here we're left over with the glycerol. And those are the chemical properties of fatty acids.